Hi guys, 16.1, justifying circumference and area of a circle, geometry. The essential question, how can you justify and use the formulas for the circumference and area of a circle? Okay, the answer is quite complex, but I can sum it up with saying as you approach infinity for the number of sides that you have for n-gon, okay, you will actually get closer to this approximation of pi. Pi is one of those natural phenomenons that just come with a lot of experimentation and practice, and I'll go into more depth as we go through. But the answer from your book and the answer that I will talk about, well, first we justify by inscribing a series of regular n-gons. Okay, so you will see this nice cute little GIF on how to do that, and you're going to see what I'm talking about. In a circle for the radius of r. Then you're going to write the expressions to represent the perimeter and the area of the circle. Then show the expressions for the perimeter gets closer to the circumference of which equals 2 pi r, and the area gets closer to the area equaling pi r squared as n gets larger, which is basically what I said here. Okay, and in fact, you'll see a little bit more of an explanation. That's just a very rough understanding of the concept. Okay, so just remember, as you approach infinity with the number of sides, you will get closer and closer to pi. Okay, so that's the rough idea. Now, to use the formulas, and you've already used them back in 8th grade, I know you have. Basically, you just have to find the radius or the diameter of the circle and then substitute and solve your equations. Okay, and again, those two equations that you'll use mostly for your homework will be the circumference equaling 2 pi r and the area equaling pi r squared. So let's get into it. So, justifying the circumference formula. So here you have this, we got, what, 6 sides? Okay, let me go ahead and, yeah, let's do that. Okay, we have 6 sides, right? We have 1, 2, 3, 4, 5, and finally 6. 6 sides. That's a hexagon. Okay, so back in the day, the ancient Greeks, when they calculated the size, I believe it was the librarian of Alexandria. His name was, wow, I can't bring up his name now. Oh, nope, Eratosthenes. There we go. He was in my head. Eratosthenes of Cyrene. He used a 50 gon to calculate the size of the planet Earth about 2,000 years ago. He was off by about 16%, but that ain't too bad for 2,000-year-old Greek dude. So, looking at it, we have this hexagon inside the circle. And as you can see, we carved out this triangle, right? Because a hexagon really is just, what, 6 triangles, right? So here we have an illustration. Basically, they're saying, and this is going off the book, triangle AOM, okay, AOM, and let me go ahead and let's use that ugly orange color, AOM, okay, is congruent to BOM, BOM, okay, and that is by the side congruency criterion. Now, right, because this guy is, well, you know, he's the he's, you know, that side is the same as that side, and for some odd reason I'm blanking out there. I'm pretty upset at myself now, but R is congruent to R, and MB is congruent to AM, right? Because it's an isosceles triangle. All right, so it's got that idea. So SS congruency, so those two angles have to be congruent, right? And that's because angle 1 and angle 2 are congruent, just like I said, right? Because if they're the same, they're the same. They're the same triangle. So the part of the part, right? So CP, CTC. All right, corresponding parts, corresponding triangles are congruent, okay? Now, therefore, there are n triangles, okay, there are 6 in this case, right, that are all congruent. Now, they all have that same situation going across all those little triangles. So, therefore, you can say, well, first off, how many degrees are there in a circle? There's 360, right? There's 360 degrees. So all these numbers of the sides are split evenly between the 360 degrees because there's, in this case, 6, but we'll just say n for now, okay? So we have n amount of sides, okay? And all of them are going to share, they're all going to divide 360 evenly, okay? So AOB, okay, this big huge angle here, okay, let me use a nice big highlighter. That whole angle, okay, just like how this whole angle, okay, they're all going to share this common theme. They're going to be 360 degrees divided by the number of sides you have for your inscribed polygon or n-gon. So therefore angle B, or angle 1, I'm sorry, and let me erase a little bit to clean this up, okay, because it's a little messy, I know. Angle 1 and 2 are going to be, 360 divided by n, but angle 1 is just half of that. Well, what's half of 360? 180. Okay, and again, I get that because originally it's 1 and 2, right? They're sharing 360 divided by n, right? But what about just angle 1? That's just half of that situation, so that's why it's 180 divided by n, okay? Now, in the triangle, the sine of angle 1 is the length of the opposite leg, which is x, and they label it here. Let me clean it up for you. Let me get rid of all this just to make it nice and clean here. Okay, they label it down here. Okay, there's our x, okay, equaling and divided by our r, right? Opposite over hypotenuse, right? That's sine. That makes sense, all right? We've seen that before with trig. So x equals r times sine of angle 1. And therefore they substitute and they get this angle for angle 1, and basically x is going to equal the r of sine 180 divided by n. Again, the reason why is because we're talking about this guy, all right, which is half of the 360 situation. So it's 180 over n. Now, that's what we used to use back in the ancient Greeks age before we started coming across this idea of infinity. And it's going to be a little bit more complicated as we go along, but stay with me, okay? You will see in the end the beauty of it. So now we're going to follow along with the book to express perimeter. Remember, perimeter, it's like adding up all the fence, right? You're adding up all of it. So in this situation, the Greeks would add up their whole outer edge to find the perimeter of their circle. Okay? So in this situation, the length of AB is 2x because, well, this guy is going to be congruent to the other triangle, so his base from MB has to be the same distance. So that's where they get 2x, okay, for AB. And that, again, is because M is the midpoint. Now, don't worry, I'm explaining to you why you have such a nice problem, a nice equation. I'm just showing you where it came from, okay? So you have to understand where things came from sometimes to appreciate what you have, okay? So this means the perimeter of the n-gon is basically going to be 2x times n, the number of sides you have, which in the book they'll write as 2n times x, or 2x times n. It doesn't really matter because multiplication is associative. So that's nice because, there's 2x here times, let's see, 6. So, we have, a lot of math there. But basically that's the idea, is it depends on how many sides we have. So now we're substituting in the expression for x from step D. And step D, so terms of R is going to be 2, and they're talking about this part right here. Okay, so you're going to have 2n times R of sine of 180 divided by n. That, ladies and gentlemen, is the original equation to find the perimeter for an n-gon. Okay, and that is a mess. Even the explanation, it gathered from trig, it gathered from congruency theorems. It was everywhere. Even the properties of circles, which was the last module we covered, that's pretty complicated. So let me show you the beauty. Okay, let me show you the nicer version of the perimeter equation. Let me get out of there first. All right, so as you can see, you have n-gons forming inside that circle. The more sides you get, the closer that number gets to 3.141259 or something like that. Pi. So as you can see, if you look really close, that n-gon, the more sides it gets, we're looking at 24, 25 sides, and it almost looks just like a perfect circle almost. Well, basically that's what the Greeks did. They just kept going and going and going until that n-gon just blurred in as a circle. But as you can see, that number is approaching pi. So this is the idea that you're getting, is based off of what I've already shown you, where your circumference, okay, your perimeter, is originally this, all right? But as the n-gons get more complex, as you approach infinity, this whole mess, all right, that I explained in my logic, it's really just turning into pi. That's where this guy, okay, turns into 2 pi r. Okay, so that is the beauty of where that formula came into. Okay, originally it was here, but thank your lucky stars that we actually went through this process of exhaustion. So you should be like, thanks Greeks for going so far into the math that you guys basically just, had this whole idea of pi. I don't think they really came across it naturally, but eventually they did, I think. But I think the Egyptians had had an idea. But again, all that mess as you approach infinity. So the more sides you have, and this is very important, the more sides you have in your n-gon that's inscribed in that circle, the more accurate your formulas will be, because you are closer to pi. So if you want to be really accurate and precise without using just pi, try a 100-side, n-gon. That's pretty accurate. So if you try a 20-gon, you'll be in the ballpark, but you won't be like perfect. Okay, so it depends on what you're measuring. All right. So applying the circumference formula. So basically, as you can see, we have a Ferris wheel, and they go ahead and give us the diameter. We already know the diameter is or the radius. Diameter equals 2 pi r. What's r? R is radius. We already know the radius should be half of the diameter. So here's your diameter, and we know that your radius is going to be half that. So what is half of 40? 20. Okay. Now we're just going to plug it into our formula. We're going to substitute. Okay. So R was 20. Okay. Plug it in. 2 times 20 is 40. And then they said to use 3.14 for pi. So we'll go ahead and use that. Use your calculator. 2 times 3.14 times 20, and you approximately get 125.6. Okay, so don't forget context. So your answer is that the circumference is about 125.6 feet. It's good to know, all right, especially for clearance. There's a lot of permits that involve this kind of math. You have to know if you make clearance or not. If you don't, the city will come in and they'll put everything on hold. You lose money while you either tear it down or shut it down, and it's annoying. Okay, but basically it's just plug and chug, just like in 8th grade. So example 2, that one's going to be on you. Okay, a pottery wheel has a diameter of 2 feet. So again, they gave you something. Okay, here's your formula. Find your radius. Okay, they do tell you the diameter, and you know the radius is what of the diameter? Okay, isn't it just whatever the diameter is divided by 2 to get your radius? Okay, so once you find your radius, plug it back in. Go ahead and use 3.14 for pi, and raise your hand. Let me know what you got for your circumference. Most of your homework is kind of this, by the way. It's nice. All right, so justifying the area formula. Well, we did perimeter, now we're going to talk about the area. So area formula works in the same sense, just a little bit more interesting. So we know that the two triangles, AOM is congruent to the triangle of BOM, okay? And we know we have some kind of n-gon, okay? It looks like a hexagon again. They didn't really complete the picture. But we do know that x is supposed to equal r sine of 180 divided by n based upon the concept we talked about with the perimeter. So if we write a similar equation for h, okay, if we were to do that, you would get h equals r of cosine of 180 degrees divided by n. So let's look at the logic of why that happens for h. So if we think about it, cosine of h, let's see, cosine of this angle would be adjacent over the hypotenuse, right? And isn't angle 2 just basically represented as 180 divided by n? Yeah, because it's half, remember, of 360 divided by the number of sides. Okay, so that's how they end up getting an expression for h. Now, using the area formula for AOB, isn't the area of a triangle, right? And this is 8th grade. Area of a triangle is half times the base times height. Okay, so that's the formula, and I don't know why my, wow, that's a really, I'm going to erase that. That is disturbing. Silly touchscreens. Okay, so that was the original equation, but in this situation, your base has 2 x's. So that's your base for this situation, and your height is just h. Okay, but remember, x is represented as this, and h is represented as this in our situation. So now that we're substituting, our area for this triangle is going to be r squared, because you have this guy times this guy, which is r squared. R times r is r squared, times sine of 180 divided by n times cosine of 180 divided by n. So as you can see, ladies and gentlemen, that is the original equation for the area formula. And basically, you have to take in consideration now, it's not just about the triangle AOB. we have 6 other triangles. We have to think about how many sides there are total. How many triangles are there total? So the only difference now is we have to add in the number of sides times everything that we had for just that one triangle. So I know it looks like a lot, but you're going to see the prettier version in just a minute. So if I can fit, there we go. Okay, so now your expression is using the factor of this. Now, what happens as the expression of n gets larger? So based off of our essential question, as the number of sides approach infinity, as you get bigger and bigger and bigger, what is this whole thing going to equal? So I'll tell you what, if you don't make it to that part, if you don't watch the rest of the video for right now and you just pause it and you think about it, I actually recommend that. What happened last time with the perimeter formula? As we approached infinity, infinite amount of sides, all that mess just turned into what? It's a very beautiful number. Pause it, okay? Think about it. All right, so you thought about it, and I'm going to go ahead and give you the answer. So let me explain. Again, same concept. As the number of sides increase and you get infinite amount of n-gons, as your n-gons get bigger and bigger and bigger, that whole mess just turns into pi. So your area formula is just pi r squared. And so that's what you use for your homework. Okay? So pi is becoming more real as we go through. And the Greeks did this. They just kept on going and going and going until they were like, hey, we're kind of leveling off at this like number. Okay? I don't even think they understood at the time what was going on. They just realized that they were just kind of leveling off. Okay? So that's going to be the formula used for your homework. So again, big, huge mess based upon this idea of inscribed n-gons. And as you can see, as you get closer and closer to bigger numbers, you're more accurate. But the less sides, the less accurate. Okay, and that's because pi is not quite, exact. So applying the area formula, example 3, a rectangular piece of cloth is 3 feet by 6 feet. What is the area of the largest circle that can be cut from the cloth? So round the nearest inch. So the diameter, so basically let me draw a pretty picture here. The diameter of the largest circle is 3 feet. They're saying inches, so I guess we'll use inches. Okay, the radius of the circle is 18 inches. So they went ahead and said there's this cloth, and basically the most you can cut out of it for a circle was 3 feet for the radius, which is basically for the diameter, sorry, which is again in inches, which was 36 inches. But the radius is half of that. What's half of 36? And that's how they got their radius. Okay, so use your area formula. Our radius we determined was 18. So you have 18 squared times pi, and you'll get your approximation, which is always going to be squared because it's area. Okay, so remember context. There's your answer. So example 4, basically you're using the area formula. Again, you have to determine what they gave you. They gave us a circular pizza measures 9 inches in length. So they gave you a pizza, they measure the length, and they tell you it's 9 inches. Well, we need to know what the radius is. And the radius is how much of the diameter? Okay, so once you find your radius, plug it back in. All right, square it times pi, and you'll get your answer. Make sure you show me, and then also remember, give me the exact measurement in context. Okay, so square inches. Let me know when you get that. Please show me. All right, buddy time. Debate with your buddy on the following question. Who is more accurate in finding the circumference or area of a circle? The person using an inscribed 10 gon, so 10 sides, or the person using an inscribed 30 gon? Why? Explain in your own words. So I want you to write 2 sentences. All right. First off, the statement. Who's right? Who's closer? And then 1 sentence explaining why. And then another sentence explaining it. Okay, so think about all those GIFs that I showed you. All right, think about what I was talking about with infinity and the essential question. And then I actually am going to draw some sticks, and I'm going to actually ask you guys to present your findings, okay? Because I think you guys need to collaborate and peer review each other a little bit more. All right, homework. It's not too much. Page 856, numbers 1 through 11. Number 1, by the way, is kind of related to your buddy time, so it's worth your time, okay? All right, good luck. If you have any questions, let me know.